the audio. That is the only problem with using the phone audio, which means the recording that I make, you won't hear that audio. So if you want to hear that audio, we need to fix this audio problem at some point. Not today, but at some point we would want to fix that. All right, so what would you like to go over today, Garrison? Yeah. Uh-huh. Okay. Why don't you go ahead and give me the problem and we'll look at it. Okay. Okay. So first of all, what is the general formula for the sine of 2 theta? Okay. So that's the best way to do this, because we already know what the sine of theta is, and we can figure out what the cosine of theta is. How are we going to figure out the cosine of theta? Draw a triangle. That is almost always the first step in so many of these trig problems. And it's a right triangle. What else do I have to do? I have to label theta. Because theta could be either the one I've labeled or it could be the top one. So if I don't label theta, I don't know how to proportion this triangle. Okay, so now that I've drawn a triangle and labeled theta, dimension this triangle for me. Okay, hold on. Let's take it one step at a time. The only thing we know at this point is this. So let's start with that. So what's the opposite side? What's the hypotenuse? Okay, now that allows us to figure out the adjacent side. And you've correctly surmised that it's 3. So we know the cosine of theta is equal to what? So the sine of 2 theta equals 2 times, what's the sine of theta? And times the cosine of theta. And that's your answer, whatever that comes out to be. What is that, 24 over 10, which is 12/5. Oh, excuse me, 24 over 25. 24/25 is the sine of 2 theta. Now, is that positive or negative? Well, the fact that it was in quadrant 1 meant that was positive and it meant that was positive. Fact of the matter is the sine of 2 theta is whatever that is. So as long as the sine of theta and cosine of theta are positive, then the answer is positive. But there are going to be some problems where the sine of theta or the cosine of theta is not going to be positive. Okay, so what else you got? Okay. equals, hold on, you lost me. Start the beginning of the equation. Cosine of x over 2 equals what? Okay. Okay. Yeah, I would do it like this, which tells you that x is in the first or second quadrants. Okay. Now, what is the general formula for cosine of x over 2? Okay. Now, notice that we know what the cosine of x is. They've given it to us over here. And that's the only unknown in that thing. So we can figure out what the cosine of x over 2 is based on what we know about the cosine of x. And then we will investigate what this plus or minus means. For the moment, we'll leave that in there. What should I put next? What goes for the cosine of x? Yeah. So that's what the cosine of x over 2 is going to be. That is a number. Okay, let's see if we can simplify that number. First of all, what's 1 minus 8/25? Okay, so we're taking the square root of 17/25. It's all going to be divided by 2, so it's actually 17/50. You with me? Now, the solution when they tell you that the cosine of x is minus 8/25, and we know that x is between 0 and pi, which quadrant is it in? Correct. So, hold on a second, let me think about this for a minute. So the cosine of x over 2 has to be in which quadrant? Take any angle you want that's in the second quadrant and divide it by 2. Yeah, in other words, x over 2, if the cosine of x is negative, meaning it's in the second quadrant, then x over 2 is in the first quadrant. As long as we know that x is between 0 and pi. So what are we going to use, the plus or the minus? Correct. Okay. Now, we're not quite done yet. I want to see if this thing can simplify. Let's see. We've got the cosine of x over 2 equals the positive square root of 17/50. Now, I know that can simplify a little bit, merely because 50 is not simplified. 17 is. In other words, I could say the square root of 17 over the square root of 50. How can I simplify square root of 50? Now, I don't know what kind of trig class you're taking. Are you taking a trig class whether they care about the denominator being irrational or not? The modern way of teaching trig is to not care. But I don't know. Yeah, because you get so many trig functions where you have an irrational denominator, and you can go to all the trouble of rationalizing it, and then if you look at the reciprocal function, you got to rationalize it again. So I agree 100% with the philosophy that you should leave answers unrationalized. But that's not to say that every teacher agrees with me. So let's rationalize this just for the heck of it. How do I rationalize that? What am I gonna do? I'm gonna multiply top and bottom by what? Okay, so that's root 34, and that's 10, correct? Okay, and I don't think there's anything else we can do to simplify that. So that would be a proper answer. In my opinion, that would also be a proper answer. Merely because I tend to agree that you shouldn't take the effort to rationalize it. Notice what happens. Now, if I asked you, what is the secant of x over 2? What's that going to be? Based on our answer for the cosine of x over 2. Tell me what the secant of x over 2 is, knowing that the secant is the reciprocal. Now you see what the problem is? Now I got to rationalize that also. So now I get 10 root 34 over 34, and then I get 5 root 34 over 17, and that becomes the answer. But it would have been a lot easier had I not rationalized the cosine in the first place. And so many trig functions are reciprocals of other trig functions that it comes into play a lot, where you rationalize one function, but you've made the reciprocal more difficult because now you have to rationalize it again. So in the last 3 to 4 years, I've seen a huge trend in trig teachers not requiring their students to rationalize functions. After all, the number is the same. In other words, that may not be rationalized, this one down here, but if you put it into a calculator, you get exactly the same thing as if you put that into a calculator. And they are exactly the same number. I'm not quite sure why math has for hundreds of years insisted that you do not have an irrational denominator. I think it has to do with the fact of how you divide things up. In other words, you can divide stuff up in half, you can divide it up in thirds, you can divide it up in fifths. But how do you divide it up in square roots of 2? Because that's not a fraction. So I think that's where the original thinking came from. I kind of wish that they would have never done it. It's just an extra step that nobody really needs to make, especially now that we have calculators. In other words, there's no problem with having an irrational denominator. So, but it really kind of have to go with whatever you're teaching, your teacher is insisting on. So what else you got? Okay. Okay. Do you have both of those memorized for cosine and sine? Hold on, let me write it out. And there is a good reason why they teach you the cosine first. What's the rest of it? Okay, that's very easy to remember, right? Now, if you look at this one, the one thing I always know is that it's going to have two sines and two cosines in it. Okay, so what is it? Actually, it's, yes, excuse me, my mistake. Go ahead. Yeah, I just do the reverse. In other words, sine of B, cosine of A. In other words, this is the only part I have to remember. And I have to remember that this is the same as this. And the reason they teach you this one first is because once you learn the first one, the second one becomes easier to memorize. Okay, so what kind of problem you have? Okay, okay. 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 All right. So what we want to do is express that as a plus or minus. And there's a couple of ways you could do it. You could do the sine of 90 degrees minus 15 degrees. That doesn't help because you don't know what the sine of 15 degrees is. It's a better way to express 75 degrees. You know both of those. What's the sine of 30? What's the sine of 45? Now just fill it straight into this formula. Well, hold on. We got to do a little bit more. What's the cosine of 30? Because we're going to need that also. Over 2. And what's the cosine of 45? Okay, now we have all four pieces. We have that one, that one, that one, and that one. We're just going to fill in. So what's the sine of the first angle? Cosine of the second angle? No, cosine is root 2 over 2. Okay. That's plus or minus. What's the sine of the second angle? And the cosine of the first angle. So what do we get? We get root 2 over 4 plus root 6 over 4. Oddly enough, this is a very common answer, which is square root of 2 plus square root of 6 over 4. Now, plus or minus. Hold on a second. Let me think about this plus or minus that's in the middle there. This was 30 plus 45, correct? So it's sine of A cosine of B plus sine of B cosine of A. In other words, we don't have that minus sign. I mistakenly put that in there. In other words, whatever you're doing in this angle here, if I'm adding 30 to 45, then I'm adding those two things up there. If I'm subtracting, if I had, say, let's say I had 150 minus 75, which you wouldn't have because you don't know what the sine of 75 is. In other words, what you want to do is you want to use angles that you are familiar with what their sine and cosine are. Because whatever two angles you make this, and it can be subtracted, it could be 90 minus 15, but 30 plus 45 makes a lot more sense because you know what the sine of 30 is, you know what the cosine of 30 is, you know what the sine of 45, and you know what the cosine of 45 is. And you have to know all four of those things to fill in the sum. And so this is our final answer, and it is plus. In other words, we know it's going to be plus because it's in the first quadrant. And you definitely do not convert that to a decimal unless the teacher specifically requests it, which they should not be doing at this point in time. In other words, once you get to trig, they want you to give an exact answer. This is the exact answer. Square root of 2 plus square root of 6 over 4. Okay? Yeah. Yeah, and yeah, I mentioned that oddly enough, this is a very common answer, root 2 plus root 6. And the reason being is that the cosine is root 3 over 2, and the sine is root 2 over 2. So when you multiply those together, you get root 6 over 4. So you end up naturally getting a root 6. As long as you're dealing with angles who is the sum of two very common angles. In other words, the most common angles you have are 30, 45, and 60, right? And when you have a problem that can be expressed as the sum of two of those angles, you're going to end up with a root 6 and a root 2. As you can see, why? Because you're multiplying sine times cosine, and then sine of the other angle times cosine. That ends up producing a root 6 and a root 2. Very, very frequently. Now, the one thing you have to be a little careful of, well, actually you don't. As long as you follow this religiously, in other words, if it starts out plus or minus, then it ends up plus or minus. And in our case, it was plus because we used 30 and 45. Had I used 90 minus 15, then it would have been different. I would have used the minus sign. But I wouldn't use 90 and 15 because I don't know what the sine of 15 is. In other words, you always try to use the angles that are 30, 45, or 60, whether it's the sum or the difference. You have any, what else you got? Yeah, I think I can. I'll try to do it as quickly as possible. Usually this takes an hour. I'm going to try to do it very quickly for you. What I want you to do is memorize everything that I write on this page. Okay? If you do that, you will be able to solve for any trig angle. Now, I call these two triangles my unit special triangles. The reason I call them my unit ones is because the side opposite the smallest angle is always 1. So that gets you started. Once you draw that 1, you shouldn't be able to memorize the other 2. Are you hearing all that interference on the phone? Okay, let's hear a bunch of it here for a second. That's okay, it's gone away. Okay, so the first thing you want to know is these 2 triangles. And notice why. Obviously, you need this also. What SOHCAHTOA and these 2 triangles do is allows you to figure out the sine, cosine, and tangent of your common angles, 30, 45, and 60. For instance, what is the tangent of 30? And no, it's, and leave it like that. Don't rationalize it. Not for me. Because we never know what we're going to do with that. Maybe ultimately I need the cotangent of 30 degrees. And if I want the cotangent of 30 degrees, it's root 3 over 1. Okay? All right. Now, let me put what appears to be an XY coordinate axis in there. Really isn't. This is polar axis. And it's called the unit circle because the radius is always 1. Doesn't matter where that radius comes. It's always positive 1. With me? Okay. So, first of all, if in blue, I'm going to draw various angles. What's that angle? Okay. What's this point right here? What's the XY coordinates? In other words, this is also an XY coordinate. Polar can be laid on top of XY coordinate. What's this one? What's this one? And this one. Now, take a look at this angle right here. Let's call that theta. Notice that that's 1. It's a radius, right? So what would the cosine of theta be? If I call this x and this y, which I would, what's cosine of theta? It's the sine of theta. So, I can take any point on the circumference of that circle, and the first coordinate is the cosine of that angle, second coordinate is the sine of that angle. So, if I made theta 30 degrees, what are the coordinates on that point right there? If theta is 30 degrees. Oh. And what's the sine of 30 degrees? Okay, those are going to be very common numbers. Root 3 over 2 and 1/2. Because it's the sine and cosine of 30 degrees. So if I wanted to know the coordinates of that point, I know it's the cosine of the angle, comma, the sine of the angle, no matter where I'm at. So tell me what the sine of 0 degrees is based on that. What's the cosine of 0 degrees? What is the sine of 90 degrees? It's cosine of 90 degrees. Okay, so you can tell that from that, you're going to be able to figure out the cosine and sine of all your common angles in the first quadrant, and you're going to be able to figure out your sine and cosine of all your quadrangles, which are multiples of 90. In other words, what's the sine of 270? And cosine of 270. Okay, so just based on what I've drawn on the unit circle here, you know how to do your sine and cosine of all your quadrangles. Those are called quadrangles. Okay? Now, the ones we want to talk about are the ones that are not in the first quadrant. Okay? All right, so first of all, let's label our quadrants in blue. 1, 2, 3, 4. When you are dealing in quadrant 2, what you want to do is you want to take your angle, whatever it is, if it's greater than 90 and less than 180, let's say it's 135. You want to subtract hold on a second. Excuse me, I got it backwards. It's 180 minus theta. So if I said to you, what is the sine of 135 degrees? And I tell you, a really good way to do this is this way, where you put parentheses, and using this formula right there, what is the equivalent first quadrant angle? Tell me what the sine of 45 is. Now, the last thing I need is to put the plus or minus on it. So there's one more thing that this page needs. All students take calculus. What that does is it tells me whether it should be plus or minus. Well, the sine of a second degree angle is what? Positive. So that's a plus root 2 over 2. In other words, the absolute value is always the equivalent of what the first quadrant angle is, and the sine follows this ASTC. Now, the only thing I've left off here is the third quadrant. In the third quadrant, you want to take theta minus 180, and in the fourth quadrant, you want to take 360 minus theta. Okay? So, now let me erase everything that is not needed, and I want you to take a picture of this page. Hold on, before you do it, let me make sure I have everything here. This is quadrant 2, and it's a C under that. And I think everything you need, you don't need these two red lines. Let me erase those. As long as you understand that all radiuses are 1. Now, everything you see on there, you want to memorize. Everything. So I would take a picture of that. Now, I do make a recording of these, although I'm not sure whether that recording is going to include the audio or not because we're using the phone. But, so if I were you, I'd take out your cell phone and take a picture of this. And then memorize it. Everything. Okay? Now, I'm gonna drill you on it right now. I'm gonna give you some angles. I want you to tell me what the sine of 150 degrees is. And do it step by step. So, the first step is let's put a little parentheses next to it. What's the equivalent first quadrant angle? So what's the sine of 150? What's its plus or minus sign? And that's the order I want you to do it in. I want you to figure out the absolute value first, And then using this ACTC, you can put the sine on it. Okay? Tell me what the cosine of 150 is. That also is the same number as the cosine of 30. What's its plus or minus sign? Okay, cool. Let me give you a few others. Tangent of 225. Now you're in the third quadrant. So first of all, tell me what its first quadrant equivalent. When I say first quadrant angle, that's the same as reference angle, in case they're teaching you all about reference angles. It's the angle that the terminal line makes with the x-axis. In other words, tangent of 225, I would draw like that. It's this angle right there. In other words, the angle that I make with the x-axis. So what is theta right there that I just drew? Okay. Now what's the tangent of 45? And the sine in the third quadrant. Hold on, you just said 1. So the absolute value of it is 1. And the only thing we need is a plus or minus sign in front of it. So let's go to the third quadrant. Tangent's positive, so we put a plus sign. So the tangent of 225 is 1. Okay, let me keep going. Let me give you some others. Cosine of 300. First of all, convert it to the reference angle. I'll call it the reference angle from now on, because that's what the schools do. To me, I always kind of think of it as a first quadrant angle, because I know how to do all of those based on these two triangles. But that's the same as the reference angle. So based on this down here, what's the reference angle? It's cosine of 60. And what's the plus or minus sign on cosine in the fourth quadrant? Nope. Because it's yes. In other words, part of this process is determining what I really should do up here is I should say that's in the second, that's in the second, that's in the third, and that's in the fourth. Because you need to know that. In order to put the final plus or minus sign on it, you need to know whether your angle, which quadrant it's in. Okay? All right, how about the sine of 420? Same process. Yes, in other words, if you have an angle that is outside the unit circle, subtract as many multiples of 360 as you can to get it inside the unit circle. And positive is better than negative. It's just easier to work with. You can work with negative, but you don't have to. So what's the sine of 60? What's its plus or minus sign going to be? Because it's in other words, that is in the first quadrant. It's once around, but it's still in the first quadrant. Okay? Let's deal with some negative angles. What's the sine of minus 30? Okay. A couple things I'm not sure they've taught you. Let's see. Have you taken a picture of this page? Okay, let me erase it all. Let's talk about odd and even functions. If I have an odd function, that's exactly the same as this. It's frequently much easier to deal with that. That's odd. If I have an even function, like cosine, then that is equal to that. Okay? And knowing these, and tangent is also odd. Those are the three you need to know right there. Because if I say to you the sine of minus 30 degrees, that's going to be the minus the sine of 30. And you certainly know the sine of 30. So what's that? And you apply the negative sign, exactly. Okay? And this is the easiest way to handle negative angles, is to use this odd-even property. So, okay, let me give you another one. Tangent of minus 225. Correct, but it was actually a three-step process, right? In other words, here's what I had to do mentally. I don't know if you did this or not, but I said this to myself. Well, that's minus the tan of 225, which is minus the tan of 45, which is, well, tan of 45 is 1, so that's minus 1. That's the thought process I went through. In other words, you have to do this conversion, and then you have to be able to figure out what the tan of 225 is, knowing that it's positive 1. All right, so what other problems do you have? Not quite sure where to go from here, so let you direct me. Okay, I'll tell you exactly. Sine is even because the graph is symmetrical about the origin. Okay? In other words, that is symmetry about the origin. Cosine, excuse me, that sine is odd because it's symmetrical about the origin. Odd origin. Cosine is even because it's symmetrical about the y-axis. If I plot the cosine, I do it this way. Notice that I have perfect symmetry about the y-axis. In fact, if I said, well, what's the cosine of 1/2? You get that value. What's the cosine of negative 1/2? You get the same value. So the cosine of minus x is the same as the cosine of x. Doesn't matter whether it's a negative angle or not. So that's the advantage, is that you can immediately treat negative angles like positive angles. Now, you don't have to do it that way. The other way to do it would be to this. If I said, what's the sine of minus 225? Well, that is the same as the sine of what positive angle? No, just take 360 minus that. So it's the same as that, right? In other words, here, I'm going to draw the unit circle. I'm going to go 225 clockwise. That's the negative angle, 225. Well, that's going to be the same as this positive angle, which is 135. they're going to have the same answer always. The problem is that when you get an angle that is like minus 30, well, it's a lot harder to do it this way, not easier. In other words, it's definitely the same as 330, right? With me? But then I'd have to go through, well, 330 is the same as 30, which is 1/2. And actually it's negative 1/2 because 330 is in the fourth quadrant. But it's much easier if you know the odd-even property rather than converting it to 330 in the first place and then converting it back to 30. I'm just going to say that this at the beginning is the same as this, and I know what sine of 30 is, so it's minus 1/2. Much easier to do it this way. I don't need to invoke this 330-degree angle. And so that's the purpose of learning the odd and even properties of sine, cosine, and tangent. And it applies to their reciprocals also. In other words, if the sine of minus x equals minus the sine of x, then the cosecant of minus x equals minus the cosecant of x. Okay? All right. What other problems do you have that maybe we can apply this to, this information? Am I correct in the fact that they are going to give you a test at some point in time on the unit circle? And the fact that they're going to ask you all 16 slots and expect you to know what the sine and the cosine are of both of them. Most every trig student that I deal with at some point is going to have to do that. What I'm talking about is this. They want to know the coordinates on that point. 45-degree angle. They want to know the coordinates on that point. 60. They want to know the coordinates on that point. 90, 120, 135, 150, 180. All 16 points around the unit circle, they want to know. So let me test you one more time. Tell me the coordinates of that point right there. The 60-degree angle. What's the first coordinate? What's the x-coordinate mean in terms of trig? Okay, good. And their test is going to want those two numbers for every point, all the way around. And you should have enough information now to do that. In other words, you still don't know how to calculate sine of 29 degrees, but you can do all 6 trig functions of all multiples of 30 or 45, including the quadrangles. I'm getting a huge echo on my end. Are you hearing it? Okay, good. I can talk over it, but if it was on your end, that might really be confusing. All right, what else you got, Garrison? Are we going to go to 4:30 or another half hour? Doesn't matter to me, either one. Okay. Okay. Mm-hmm. There's that graph. And this is, or you're into radians, right? Okay. That's pi over 2. That's pi. That's 3 pi over 2. That's 2 pi. Now, in reality, that curve goes on forever, just repeating itself. But the most important part of it is just the one cycle. In other words, we can do virtually all of our trig based on this part of it right here. Now, its relationship to the unit circle, one way I've heard it explained that is kind of interesting, not sure I like it, but it's if you grab that point and you pull in that direction, you get that curve. It is not necessary that you correlate between the two. In other words, you don't have to know the correlation. What you have to know is the graph. In other words, you need to be able to draw the sine curve, you need to be able to draw the cosine curve, and you need to be able to draw the tangent curve. That's another thing you want to memorize. Cosine goes like this, and notice that if you know these curves, you actually can answer the quadrangles easier. In other words, I know that's pi over 2. I know that's pi. I know that's 3 pi over 2. So if I said to you, this is the cosine, what's the cosine of 3 pi over 2? Read it off my graph. Yeah, 0, exactly. In other words, you can do it from the unit circle, but to me, it's the hard way. Because you've got to memorize these two curves anyway. You really do. They're not going to let you out of trig without memorizing these two curves. And once you memorize those two curves, then all your quadrangles are evident from these two curves. It's not so clear as to what the sine of pi over 4 is. I don't know what that is without my two triangles, but I certainly know what the sine of pi over 2 is. It's the peak, which is 1, and the trough is minus 1 for both sine and cosine. Now tangent, it's a little significantly different. Tangent actually has a range from negative infinity to positive infinity, and it goes from minus pi over 2 to pi over 2, and it has asymptotes. In other words, there's no such thing as the tangent of pi over 2. It's infinity. And the tangent of minus pi over 2 is minus infinity, because there's a vertical asymptote there. There's another vertical asymptote at 3 pi over 2. In other words, every pi on the tangent curve, you have a vertical asymptote. And each curve is like this. It's always increasing, always approaching those asymptotes. So the tangent is a lot different than the sine and the cosine, even though the tangent's equal to the sine divided by the cosine. And you can kind of see why there would be an asymptote at pi over 2, right? In other words, if tangent is sine of x divided by cosine of x, whenever cosine of x is equal to 0, which is at pi over 2 and 3 pi over 2, then tangent of x is going to be undefined because you can't divide by 0. So that's why we have these vertical asymptotes at pi over 2 and 3 pi over 2. That's where cosine of x is equal to 0. So it all makes perfect sense algebraically. Garrison, do you have any other specific problems that you have questions on? Okay, well, hopefully this has been helpful to you, and I'll talk to you next time. Well, good. I'm glad I could be helpful. Garrison, you have a good evening. I'll talk to you at our next session. Oh, okay, bye-bye.